See, I'm going to state a result which was proved by one of the students in ISI Chennai. The result is the following theorem. I'm not going to prove it, but I'll just tell you what it is. Let A equals minus A transpose 2m plus 1 cross 2m plus 1. Then the two in the following two conditions are equivalent. One, A is completely mixed. That is, all optimal strategies are completely mixed. Two, A plus di is a Q matrix for I is equal to 1 to n, where di is a diagonal matrix with ith diagonal 1 and other diagonal 0. So this is the result. I don't know how many of you know the, you know, huh? Oh, okay, we use the diagonal matrix, only ith, the other rest are all 0. See, only ith row contains one positive entry. The rest of the rows are 0. That's what I'm saying. Okay. Do you know what is a linear complementarity problem? Any idea? Oh, it's better to explain. Okay. Otherwise, I thought of doing something which will be interesting for mathematics people. But anyway, I'll come to that later. Yeah, I'll give you the definition and then I leave it. This is done by myself and Ravindran and his student Yadav. So this is another characterization of the completely mixed. The only thing I have to explain what I mean by a Q matrix. Okay. See, since there are some mathematics professors in the audience, I thought I'll tell some result which will be of interest to them. Okay, first let me give you the definition of. See, suppose I have a matrix M, which is a square matrix, or n cross n, and Q is in Rn. So I have a matrix M and Q in Rn. The linear complementarity problem associated with MQ is the following. Find, if possible, a non-negative vector x in Rn plus, this means the non-negative orthant, such that mx plus q is also a non-negative vector with x transpose mx plus q is 0. Such a problem is the linear complementarity problem associated with given matrix and Q. Given an M and a Q, the linear complementarity problem is to find an X non-negative, if possible, of course, such that the vector mx plus q is also a non-negative vector, and these two vectors should be orthogonal. That's what it means. Since it is non-negative, this condition is equivalent to saying xi transpose mx plus q, I'm sorry, xi into mxi is 0 for all I equal to 1 to n. Now, because x is non-negative, this is also non-negative. The inner product is 0 means xi, yi must be 0. And that's what I'm writing. Okay? Because both are non-negative. So the individual thing should be. So this is equivalent to this. See, for example, if I take a matrix M with all entries negative, and if I take a Q with all entries negative, you are not going to get a solution. Because mx plus q will never be non-negative. So only certain matrices will have. So what I mean by a Q matrix is the following. Suppose, and such an X, I mean, if you can find, is a solution to LCP M comma Q. If you find an X, okay? Okay. Suppose LCP M comma Q has a solution for all Q in Rn, then I call such a matrix, then we say M is a Q matrix. M is Q. For every Q, there must exist at least one solution. Then such a matrix is. In fact, one can check if M is a positive definite matrix, it will have a solution. And if M is a strictly positive matrix, by that I mean if all the entries are positive, then also it is Q. There are many examples of matrices which are Q. Okay, that's the definition of this. So what I stated in that theorem is, if you take a skew symmetric matrix of odd order, the game is completely mixed. By that I mean all optimal strategies are completely mixed, if and only if the matrix M plus di, di is a diagonal matrix with ith diagonal 1, the rest are all 0, is a Q in this sense. Okay, that's it. Now let me go to any question? No, we don't use Kaplanski's theorem. Here we don't, but I can add that also as a third condition. No. We use the following theorem due to Cartle. That is, if you have a P naught matrix, it is Q if and only if it is R naught matrix. Because I have to enter into too much on LCP, which I don't want. Instead, I will prove some result I have shown in the class. You might have heard me talking, and so that some of them may be interested. So I'll do that. Because this LCP is a special topic. See, the reason why this problem is studied is the motivation for this problem is the following. When you look, I mean, so you might have seen Nash theorem, isn't it? Prisoner's dilemma or something like that, you must have heard. To find a pair of equilibrium point for a bimatrix game is a hard problem. Because when Nash proved it, he proved the existence using the Brouwer's theorem or the Kakutani's fixed point theorem. But later on, Lemke and Hausen, his student, they gave a beautiful algorithm for solving that problem in a constructive way. That is, if you follow their algorithm, you can get a pair of equilibrium points. In other words, they gave a constructive proof to get a pair of equilibrium points. That is the motivation. That is how this subject arose actually. The linear complementarity problem arose from game theory actually. Because I have not said anything about the bimatrix game or etc. So the origin of this problem comes from a game theory, which was developed by Nash. Okay. All right. Now let me state a theorem which is due to, I think, some Russian, if I'm not wrong. It's a very nice result. Let me state the simplest result and then I'll take you to a slightly more general result. Take the unit interval 0, 1. The question is the following. I pick finitely many points, x1, x2, etc., xk. All of them come from 0, 1. The question is the following. Question: can you find a y in 0, 1 such that the average distance of y from each one of these points, that is 1 by k summation mod xi minus y. This is the distance because you are in the R1. So this is the distance. I is equal to 1 to k equal to some constant c. You find a y and a constant and a c such that. Let me tell you the problem precisely. This k could be 2, this k could be 3, this k could be 100, it can be 10,000, whatever it is. Can you find? Of course, this y will depend on the number of elements. I mean, this y will depend on the collection you are choosing. It will vary according to the collection. And this c will not depend on, it will depend only on the space and the metric. It's a universal constant in the sense that if you change the metric, the c will change. Here I am using the usual metric, Euclidean metric. Between any two real numbers, the distance between two numbers is the absolute value. I mean this theorem, you can prove it for the BSc student once I tell you the proof. What does your intuition say? Can you find the next? Okay, let me tell you. Suppose I choose 0 and 1, just two numbers. This is my collection. Okay. I want to find a y that is in the interval. That is, I am picking this point, the end point, the extreme point. I can, whatever you choose, any point y, the distance between 0 and y is y. The distance between 1 and y is 1 minus y. There are 2 points, so I divide by 2, which is half. So you should try, the constant c should be somewhere near half. Is that clear? Because if I choose 2 points, it should not depend on the collection, that constant. It should depend only on the metric and the space. So here, if I choose 0 and 1, for example, if I choose just the 1 point, namely 0, then then the y will be half. Okay, suppose I choose 3 by 4, singleton, then the y will be 1 by 4. Am I right? Because there is only 1 point, so distance between 1 by 4 and 3 by 4 is half. So the constant is half. That much is clear. So the question is the following. Given a finite collection of points, can you find a y such that their average distance equal to half? That's the question. Once I tell you the proof, you will see it's a very simple thing. You can tell this to a BSc student. The proof goes something like this. Suppose you are given a finite collection of points. I'll tell you how to find the y. First, this is given.
So in this problem, whether the c is already given or that.
What do you say?
C, the constant.
No, in this case, I'm telling you, in general, that will be a problem to find that c. You may not guess, but here you can guess.
So what is the input? Only the k real numbers between 0 to 1.
K could be 2, k could be 3, anything. But I know I will try for half. C is equal to half. Okay, I'll tell you why. Because, don't you think so? Because if I take 0, 1, if the average is half only, so C should be half. In this case, at least you can guess. But in general, it's not easy to guess.
But even I could not understand the problem.
Okay. Take any finite collection of points. Finite collection, each one of them is a number between 0 and 1. Can
finite set is fixed or it is also varying?
No, k could vary. K could be 1, k could be 2. No, k could be 3, anything. Okay, k could be anything. And not only that, this x1, x2 can also repeat. x2 can be equal to x1 also. There is no problem with that. Given this collection, can you find a point y in the interval such that you calculate the distance of y from each one of these points? Take the average, will it be equal to half?
So the constant will not depend on the choice of,
No, it don't depend on how many points you choose.
even if we change.
Yeah, even if we change the constant, that's what I'm saying.
That is the set.
Yeah, you can change the correction. Still,
The same
from the way I showed you, it should be half. I mean, intuitively you can guess. Okay. All right. See, this correction is given. Okay. Now, what I do is the following. I define a new function, define g from 0, 1 to 0, 1 as follows. This function g, I am going to make use of this x1, x2, x3. 1 by k summation. Suppose I pick a point z in this interval, z I am writing. G of z is this. Z minus xi, I is equal to 1 to k. So given this collection, I am defining a new function which maps 0, 1 to 0, 1. G of z is any point in the interval 0 to 1. Because this collection is given, I can calculate this, take the average. That's my g of z. Is it clear? It is a continuous function. So this function, this is a function from 0, 1 to 0, 1 because once z and x are in 0, 1, the absolute value will also be in this. So it's an average will also be. So g is a function, continuous function from 0, 1 to 0, 1. Is that clear? Okay. Now calculate g of 0. G of 0 is 1 by k summation xi, I equal to 1 to k. Because I am going to put z equal to 0, mod xi is nothing but xi. Xi's are all non-negative, so this is equal to x bar, the average of these numbers. Okay, g of 0 is the average. All right. Now I will also calculate g of 1. G of 1 is 1 by k. 1 minus xi is simply 1 minus xi. Summation 1 minus xi, I is equal to 1 to k. All right? Because 1 minus xi modulus is simply nothing but 1 minus xi because 1 is the highest.
1 minus x bar.
So this is, yeah, right. That's right. Excellent. 1 minus x bar. So what is g of 0 plus g of 1? That is equal to 1. Okay. So there are two possibilities in this case. G of 0, 0 less than or equal to g of 0 less than or equal to half, or g of can I say this? Or 0 less than or equal to g1 less than or equal to half. Because both cannot be greater than half. Then g of 0 plus g of 1 will exceed. So either the first one or the second one must happen. Okay. Suppose g of 0 is less than or equal to half, then g of 1 will lie on the other side. So g of 0 less than or equal to half, less than or equal. Since it's a continuous function, there is a 1. That's it. Mean value theorem. That's it. That's the proof. It can be told to BSc student. There is nothing. Given any finite collection, you can always construct a function g. The construction comes from the given collection. Okay. So this is the proof. Now the question is the following. Suppose I go to a different, for example, let me raise the following problem. Because you may be asking, game theory, is it related to this? Yes, I'll come to that later.
In this problem itself, if you change the size of x to x.
It doesn't matter. Y will change, that's all. I will consider a new function, that's all.
The same function, whether we will.
No. It depends on the, see, given the finite collection, I define the function g. G will depend on x1, x2, x3. Yeah.
So this Y and C will also
This Y will change if you change the X case, X1, X2. Of course,
C will also change.
C will be half. C will not change.
C will not.
C will not change because the same argument for that also. Yeah, metric change. Yeah, that will be a problem. Yeah. Okay. Now let me ask you the following question. Take for instance the equilateral triangles A, B, C. These are the vertices. My set is this. Okay. Suppose I choose correction of points. Does there exist a C such that the average distance is C? Here it is not clear what C is. You agree? Not only that, I can even take this set. I can take only the sides of the equilateral triangle with the unit length. Okay, I can ask you the following question. Suppose I pick points only on the boundary. Can you find a point on the boundary such that the average distance is? So I'm going to write a general theorem and tell you some kind of a proof for that, okay, using game theory. Of course, this is a very tricky problem to find the C. It's not easy in general. Okay. This is a theorem. I think it is due to some Russian mathematician. I don't remember exactly, but I think so. I'll state it in general, but let XD be a compact connected metric space. Then there exists a unique constant C. This constant C depends on the space X and D. The C will depend on the space and the metric that you use. You can see with the following property. Given any finite collection of points, given x1, x2, etc., xk from x, there exists a y which will depend on this collection such that y in x, of course, 1 by k d xi y I is equal to 1 to k equal to c. This is the theorem. It is true in general in any compact means closed and bounded. That's what it means. Connected means, you know the definition. It cannot be written as the sum of, union of two open sets. Okay, so let's see. Then the same result holds good. Okay. The proof is, the original proof by the Russian mathematician is somewhat different, but a very nice proof using game theory was given by Oliver Gross. This appears in Advances in Game Theory, 1964, Princeton University Press. So I'm going to tell you something about it, how game theory is related to this. Of course, I'm going to talk here a game which is slightly more general, which is more general than the matrix game. So first, let me give you the description of the game in this case. The game is the following. Player 1's Pure strategy space is the given compact connected metric space. He picks up, okay? And player 2 also is the same. Y, which is the same as X. I denote it by Y, which is the same as X, to distinguish the two players. Now, player 1 picks an X from capital X, and player 2 picks a Y from capital Y. The reward for player 1 is the distance between XY. Okay? dxy is the payoff. And both choose simultaneously, remember. They are not, so it's a game with imperfect information. So let me repeat. X is chosen by player 1 and simultaneously Y is chosen. Let me give you an example. For instance, let us take this 0, 1 interval. This is a closed bounded interval. The distance is between any 2 points is X is chosen, and this is also Y. So dxy in this example is mod X minus. So that is a payoff. Player 1 wants to maximize and player 2 wants to minimize. And instead of playing a pure strategy, player 1 can use some probability distribution in the interval 0 to 1. Any probability distribution will be a mixed strategy. Because in the case of the matrix vector, because there are only finitely many rows and finitely many columns. But here, this 0, 1 interval contains infinitely many points. So you have to use probability distribution. So mu is a probability distribution. You can choose the uniform distribution or you can choose beta distribution, anything. But probability distribution. The total integral should be equal to 1. Or you can mix also. Partly continuous density, the other part can be discrete. And then you can combine any kind of probability distribution. So one can work out. So let me denote by, let me come here, d mu lambda, where mu is the probability distribution on the space X and lambda is the probability distribution on the space Y, which is nothing but on X, such that this is nothing but, by definition, you integrate the function dxy with these probability distribution, d mu X, d lambda Y. This is over X, this is over Y. This integral is well defined because X is a compact space and dxy is a continuous function, so it is bounded. Okay, so this integral is well defined, so you have no problem. For any probability distribution mu comma lambda, this is well defined, so no problem about defining this. So this is the expected pay of player 1. Player 1 wants to maximize and player 2 wants to minimize, as in the case of the matrix theorem. So here the minimax thing is the following: max over all possible distribution, and then player 2 minimizes lambda, d mu lambda. Or the other way out, I can interchange minimum over lambda and then maximum over mu, d mu lambda. And one can show that these two are equal, even here. This result is due to, you can prove it. You can use any one of the minimax theorem. For example, you can use, for instance, this essentially due to Irving-Glicksberg. Or you can use also the minimax theorem due to Sion, because they have proved some more general minimax theorems compared to von Neumann's minimax theorem. So you can use any one of them and do this. The constant C which you are looking is identified with this value. That's the result of Oliver Gross. Okay, the C is this. That is a major result of Oliver Gross. He identifies. See, there they say there exists a constant C, but he actually identifies the constant C with this. But it is not easy to find the value of the game in a given situation. And let me tell you some problems here. Let me go back here and give you the constant. Of course, here you have to use some measure theoretic results in the sense that how can you write maximum over all possible probability distributions? But that is a well-known result in the theory of probability. That is, if you have a compact metric space and if you look at the possible distribution, probability distribution, you can show that it is also compact and metrizable in a certain topology called the weak topology. These are all well documented, and you can see any measure theory proof or any probability book, it will be there. One reference I can think of is K.R. Parthasarathy's book on measure integration. It is very well discussed. Okay. All right. Now let me try to work out two specific examples. But it is not easy to construct this constancy, and people working in computer science, they are trying to find this. Okay. This C is not easy to compute in general. Okay. I'm going to look at two examples. Maybe if time permits, I'll look at the other example. Okay. And also I'm going to demonstrate that why the constant depends on the metric. Okay. I'm going to take the simplest one. X is 0, 1. And y is also 0, 1. And dxy, this is example 1. Example 2, the space will be the same, but here the metric is dxy equals modulus x minus y. Here I will change the metric. dxy is positive square root of modulus x minus y. See, in the first one, my metric is mod x minus y. In the second one, my metric is positive square root of mod x minus y. That is x minus y modulus raised to the power half. It can be also written like this. This is equal to mod x minus y power half. You understand? This is very different metric. Okay, first let me show you it's easy to calculate in exercise 1. Exercise 2 is a bit hard. This is done by Blackwell, David Blackwell, the second one. I think it is the paper appears in one of the Berkeley Symposium volume, I think. I'll also tell you a brief history about the second problem later. This is called the square root game. Because one can also look at square root, I mean, instead of this, you can also look at x minus y modulus raised to the power a, where a is any number between 0 and 1. Equal to 1, I am looking at, a equal to half, I am looking at this. You can take your metric to be this also. But I am going to discuss only when a equal to 1 and a equal to half. Okay. A equal to half is the one very well discussed in Blackwell's paper, which is called the square root game. Okay. All right. Let me first discuss this one. Can anyone make a guess about this? We told something in the last lecture. Also, we have proved something. Isn't it half or something like that? So half will be the answer even here. The reason is the following. Here the constant is half. Why? See, I take a distribution like this. I take 2.01. So here I take half with probability half. That's what I distribute. I take a discrete distribution. That is 0 with probability half, 1 with probability half. That's my strategy. I'm claiming that this is an equalizer strategy. What it means is the following. I'm going to calculate, let me denote this strategy by mu naught. What is d mu naught y? D mu naught y equal to half of d0 y plus half of d1y, which is equal to half for all y. Because this is going to give me y, this is going to give me 1 minus y, y plus 1 minus y by 2, which is half. This is true for any y. So in other words, this implies, these two together implies d mu naught comma lambda. That is, if you integrate this function with respect to any probability distribution on y, since this is constant, lambda is a probability distribution, d mu naught lambda is also equal to half for any lambda. Lambda, I'm sorry, half for all lambda. See, such a strategy is called an equalizer strategy. That is, if player 1 uses mu naught, no matter what the other player does, he gets at least half. He gets exactly equal. Now, since the function dxy is symmetric, dxy is the same as dyx, for the other fellow also the same thing is going to work. That is, what I'm saying is dx comma, I will use lambda naught. Lambda naught is also the same distribution. Lambda naught is this. Lambda naught is the same distribution. So this is also equal to half. By employing lambda naught, player 2 is not giving you more than half. So the value of the game is half, and that is precisely the value, the C you are looking at. Is that clear? So any strategy of this type, they are called equalizer strategy. Mu naught is an equalizer strategy which gives the value, and x lambda naught is an equal, but both are same, and therefore the value of the game is half, and that is precisely the C that you are looking for in the Gauss theorem. Okay, so for the first one, the answer C turns out to be half. This is equal to half. The second one is a more complicated. It's not as simple as the first one. Do you think it will be more or it will be less? Can you make any guess? The C that we are looking at. Huh? Maybe less. Any other comment? Or somebody says more? Okay, anyway, whatever it is, let me tell you what it is. I can give only approximate. I can't give you the precise answer. But actually it is more. That's the thing. See, that's the logic. What he says is right, isn't it? The square root, because it's a number between 0 and 1, so this gives you more. So naturally, you would expect more. Correct, you are right. That logic is the best. Because square root, that's right. Okay, I won't get into the full details, but see, what you can show is, or shown in the paper of Blackwell is the following. It's a very intricate argument, but you have to see. See, what he does is he integrates this dxy with respect to d mu naught of x. This is some identically some constant. This is the C for all y. And similarly, since this is also symmetric, dxy d lambda naught, of course lambda naught is the same as mu naught, y is also identical equal to Z. He was able to determine mu naught and lambda naught. I mean, mu naught, once he finds lambda naught, symmetry, so the same thing. This lambda naught is the same as this. So C is the thing. Okay, this has a history. This problem has history in the sense that, but first of all, how did he come to a distribution mu naught? What is the distribution? See, this he gave us an exercise for the students when he ran the course on game theory in Berkeley. Several students used in those days only hand calculators were available. Okay, it was in the 50s or something like that, or maybe. So, see, one way of attacking problems of this type is to discretize it and then take the limit. That will give you the value. That is what I'm saying is, you can take, for instance, two values, for example, 0, 1 and 0, 1, each player. Now I can construct a matrix here, 2 by 2, 0, 0, 1, 1. So now I can write down the matrix here. So if both players use 0, what happens? X minus y is 0, so this is 0. If one player uses 0, the other player uses 1, this is 1, square root of 1, which is 1. 1, here also it is 1, it is 0. So the value, this is V1, this is the first approximation. V1 is half. The value of this matrix here is half. Okay, you can easily check. Now let me take 3 points. For instance, I take 0, half, 1. Now I have a 3 by 3. 0, half, 1. 0, half, 1. So this is 0, this is 0, the diagonals are 0. Now suppose 0 half, then what happens? 1 by root 2. Here what happens? This is 1. Am I right? Yeah, okay. Here it is 1 by root 2. What happens here? 1 minus half, so 1 by root 2. Here it is 1, 1 by root 2, 1 by root 2, like this. So you have to find the value of this gain. And now next you go to 4 points. 0, half, 3 by 4, 1, like that. The next one you take 0, 1 by 4, like that. If you have a small calculator, you can do all this. So the students went up to 20 by 20 matrix. As a group they worked, and then they found some sort of a beta distribution which is giving you almost close to the constant. They were not able to prove it. A beta distribution is a probability distribution which is of the following type: some constant into x to the alpha minus 1, 1 minus x to the beta minus 1. Am I right? Or something like that. Alpha and beta are greater than 0 or something. That constant is, you write in terms of the gamma form. I'm not writing that constant, so that you make it 1, probability distribution. So they were able to, they went up to 20 by 20, which is a very heavy calculation. Now maybe it is easier because of your computers. They did it. And then Ferguson, who is another statistician, he also worked on it, and he found out the value as 0.59, approximate value is something like 0.599. He went up to 3 or 4 digits. But then they were not able to establish precisely what that beta distribution is. He identified the precise beta distribution with something like alpha is equal to 1 by 4 and beta is equal to 1 by 4 or something like that. That distribution, that is a precise distribution. He proved mathematically that C, for that beta distribution, it is precisely the constant. Same thing for them. And therefore, C is the value of the game. But now I know that, I know the beta distribution. I can write mu naught precisely with alpha is equal to 1 by 4 and beta is equal to 1 by 4. And now put y is equal to 0. I can calculate this integral. Blackwell does it. And he gets up to 7-digit 0.59 and something. He finishes. So the square root game is a more difficult game. Maybe, I mean, you have to see the volume in which he has published. Maybe in the 50s or something like that. Early, either late 50s or early 60s. Before I joined to teach there. Yeah. No, Ferguson used his hand calculator and then he was able to compute. So, Blackwell and Ferguson wrote a beautiful paper in game theory. Yeah. I mean, on stochastic game I'm talking. This is a very, very important paper to solve some important problem which was left open by Shapley. So here you put, because this is true for any y, so I can take actual y equal to 0. So this is nothing but dxy is nothing but x. X times this. In other words, you have to compute the expected value of that beta distribution. You know that. So something like that. They were able to do that. So this problem, so it has a I mean, you know how game theory comes to rescue to, even though initially it was known there is a constant, but they were able to identify with the value of the game with the distance function. Okay, now let me take that and I will tell you how. See, the several papers have been written after Grass's work. One Australian, or maybe a couple of them, I don't remember, it appeared in the American Mathematical Monthly, if I'm not wrong. They were able to calculate the constant C for this thing. I don't remember the constant, but let me tell you what they did. So I have the equilateral triangle. The space is only the boundary of this A, B, C. My x is the boundary of the equilateral triangle. Triangle ABC, and each side unit length. Want to calculate the constant C. What is C? Okay, that's the. Okay. See, first, initially, they take 3 points. Okay. The midpoint of the sides. These are the 3 points, midpoints. So let me say Z1, Z2, Z3. Each one will have 2 coordinates. It is in the plane. So there are 3 points. Z3 is the midpoint of this side, and Z1 is the midpoint of this, Z2 is the midpoint of this. Now they define a function h of z equal to 1 by 3 d z comma zi summation I is equal to 1 to 3. I mean, just like we did in the 0, 1 case, they define this. Okay. And I know from Gross's theorem there is a constancy. That I know. Existence I can always assume, and not only that, that is unique. That also I know. Okay. All right. So there is a Z naught, there exists a Z naught such that 1 by 3 d Z naught Zi equal to C. Okay. Suppose the Z naught is some point here. Suppose this is a Z naught. Okay. Z naught is that point. Okay. Now I drop the perpendicular. Okay. Or maybe they are taking the vertices, I'm sorry. Z1, Z2, Z3, initially they take the vertices, sorry. Because the other one I have to construct, I mean, similar function, but I think I'll do for the vertices, that's easier. Okay. So my 3 points are this. This is Z1, this is Z2, Z3. So see, I'm taking the 3 points, simply the vertices, and then I'm constructing this. So this is. So Z naught could be anywhere in one of these sides. So suppose it is here. I think Okay, that's okay. You have any problem? The Z naught. See these two, I mean d Z2 Z naught plus d Z naught Z3 is simply 1. Okay, this is equal to 1 by 3 1 plus d Z naught Z1. Am I right? See, because d Z naught Z2, which is this distance, and d Z3 Z naught is this distance. When I add, I know it is of unit length, so I put that and with this. So this is your C. Can you calculate by any chance d Z naught Z1? Can you get some approximate value? That's what they do, I think.
We have
Some number. Can you find out that?
the
Where?
top.
Yeah.
Distance is a is 1 by 2 of
Okay. Okay.
Z naught.
So I will get some kind of an estimate.
No,
That is, in other words, this C will be greater than or equal to, let me see. Okay, you are right. This is greater than or equal to 1 by 3. I think that's how they do, I think. 1 plus, let me call this number M, midpoint, okay? D Z1, Z0, Z1, D Z1, M. Am I right? And DC1M I can calculate. Root 3 by 2. Okay? All right. So this is equal to 1 by 3 into 1 plus root 3 by 2. Whatever it is. I mean, okay? This is one estimate. That is, he gets C is greater than or equal to. Similarly, what he does is, he is taking another 3 points along the midpoint of the sides. And then there must be a Z prime such that 1 by 3 that equal to C. And then he shows the maximum value of that function is at most 3 plus D. So C is this. That's all. C is precisely this. The irrational number enter the picture. And not only that, they make other calculations also. I don't know. I mean, they use some computer and get it. For example, if you take the unit circle and take the circumference as your x is the circumference of this, then in that case the C turns out to be something like 2 by pi or something. Some strange numbers appear. And what happens is, they also observed, of course they went up to some dimension. It is in dimension 2. In dimension 3, it is a regular number, not transcendental or algebraic. It's a regular number, some 4 by 3 or something like that they calculate. And when you go to the dimension 4, again the pi appears. They are asking whether is it happening in given dimension that pi, or they don't know the answer. They leave it there. Yeah, anything? Ah, okay. So this is the type of problem. Oh, I mean, here the way you calculate C, you have to use different kind of methods. In the sense that same thing. I mean, in 0, 1, what you did was maximum. There it is easier. When you go to higher dimension, you don't have such a theorem to tell you the answer. So you have to use different kind of functions. The first function gives you the estimate C must be at least this. In the next one, you will get C should be at most the same thing. So that's the value of this thing. Okay. Let me just give you a brief introduction of the Nash. Without Nash, game theory is not complete. You know, all of you must have heard that name. I mean, so let me, Nash is a pure mathematician actually. And he wrote a thesis in 1950, published it in 51 or 50, something like that. One of the shortest theses submitted to the Princeton University, and he went and presented this to von Neumann. Von Neumann simply made a remark, yeah, it's an application of fixed point theorem. He doesn't realize the significance of this theorem at that point. It's true, it is just an application of fixed point theorem. That's true. But later, many people refined this and it is found to be useful. So let me tell you the theorem of Nash without getting into the, I will tell it in terms of the matrix. That will be easier for me to do that. You have two matrices, A, comma B. Both are of the same order. A is M cross N and B is also M cross N. So I will this is the definition of the equilibrium point. Let me state the definition. Call x naught comma y naught an equilibrium point if x naught transpose a y naught is greater than or equal to x transpose a y naught for all x, in the space of probability vectors in M space, okay, and x naught transpose b y naught is greater than or equal to x naught transpose b y for all probability vectors, for all y probability vectors. Okay, that's the thing. Of course, both try to maximize. That's the thing. That is, the interpretation is very simple. If player 2 is using y naught, there is no incentive for player 1 to deviate from x naught because that gives him the maximum. Because both try to maximum. I assume that both want to maximize. Both want to maximize the income. Similar, yeah, go ahead. Not necessarily. No, this is true in general. Yeah. Any rectangular matrix, yeah, there is no problem. Yeah. Because x naught transpose a y naught is a number, because you can do that, because m by n, this is m coordinates, m row, so you can do it, and y naught as n coordinates, so this is a number. This number is greater than this. Similarly, so this is the, and here also one can define the notion of completely mixed equilibrium. That is, every equilibrium is completely mixed, where this x naught is a completely mixed strategy and y naught is a completely mixed equilibrium. Okay, so that's, and Raghavan has studied what Kaplansky did for zero-sum games for the bimatrix game. Of course, he could prove only one side of the story. If this is completely mixed, he was able to show the matrix must be square and things like that, rank n-1 and things like that. The other way is not possible in the bimatrix game. So what my student did is the following. The following question was raised. See, it is quite possible that A and B may be completely mixed in the zero-sum sense. Okay. For instance, let me tell you some example. 1, 0, 0, 0, 1, 0, 0, 0, 1. This is my A matrix. And let me take the same as B also. Okay. Here, there are many equilibrium points. But as a zero-sum game, each one has a unique, completely mixed optima. So this pair of bimatrix game is not completely mixed. Because B also this. 1 0 0 0 1 0 0 0 1 because A11 is greater than or equal to 0 0 0 and similarly the B11 is greater than or equal to this entry. So here what happens is there are many equilibrium points in the sense of Nash. Of course, this is a pure equilibrium. This 1 1 1 is a pure equilibrium, 2 2 is also a pure equilibrium, and 1/3 is also a pure equilibrium. I mean, completely mixed equilibrium. So, but as a matrix game, they are completely mixed. Is it okay? Now the question is, if these games are completely mixed, when can you say the bimatrix game will be completely mixed? That is a question one of the students wrote a master's thesis. That is related to the Pfaffians. So I thought I should mention that. Of course, it is very special in the sense that when n is equal to 3, he was able to do it, but when you go to higher dimension, it's not clear. A as well as B both are in R33. Because as soon as I said Pfaffian, it has to be skew symmetric. Otherwise, there is no hope. Both are A is minus A transpose and B is minus B transpose. Okay. And I'm going to assume that these games are completely mixed. This is completely mixed. In the usual sense of Kaplansky, this is also completely mixed. So this is going to have 3 Pfaffians, P1, P2, P3, and this one will have Q1, Q2, Q3. Okay, is that clear? I am taking a 3 by 3 completely mixed skew symmetric game. The theorem is the following. Bimatrix game A comma B is completely mixed if and only if P1, of course we know that P1, P2, P3 alternate in sign and Q1, Q2, Q3 alternate in sign. That we already know by Kaplansky's result. This is the thing. Pi, Qi is negative for all I. So this is the result. Because that already, I mean, once you assume that P1, P2, they alternate in sign because that game is completely mixed. That is what I'm saying is in the 1-0-0 thing cannot happen in the case of the skew symmetric game if it is completely mixed. Provided this. I mean, let me tell you why we need this condition. It's very easy to construct an example. Suppose I take A equals 0, 1, minus 1, 0, minus 1, 1, 1, minus 1, 0. Suppose I take A is equal to B. Now here, what are P1, P2, P3? P1 is, omit the first row and then this is 1. P1 is 1, P2 is P1 is 1, P2 is minus 1, P3 is 1. I guess you are seeing this. By P1, I mean you omit the first row, first column, you take this 2 by 2. Phi is whatever is there. So that is plus 1. P2 is omit the second row. So minus 1. So they alternate in sign. So it's for B also it is the same. Q1 is 1, Q2 is minus 1, Q3 is plus 1. But this condition is violated. P2 is minus 1, this 1. No. For a 2 by 2 matrix, 0, A minus A, I'm not assuming A need not be positive, it can be negative. So phi n of this matrix by definition is this A. See, the determinant is A square. I will take the sign to be whatever is there. If it is A is positive, it is positive. A is negative. Okay, that's all. For 2 by 2, that's how we define. Now this game is, individually they are completely mixed because of Kaplansky's theorem. But bimatrix game is not completely mixed because the number 1, that is 1, 2 is an equilibrium point because 1 is bigger than 0, 1 is bigger than minus 1. 1 is bigger than 0, 1 is bigger than minus 1. So it's a pure equilibrium. So it's not completely mixed. In other words, if you don't assume Pi, Qi less than 0, the result fails. Even for this, you have to go through some arguments. I won't go into that. Okay, so that's I thought I should mention this. Yeah, okay. Thank you for being patient and listen to what I said.